All right, so neural networks. Question? How much time do we have? Half an hour. So you have the videos, the hands-on homework help videos. From right now, since the process of neural network is so complex, the videos are not only helpful for homeworks, don't wait till the last minute, but use that data set for those videos and try to follow, step by step. Try to understand the purpose of different lines. And then if you have more time, energy, and curiosity, try to dig, understand, one more level about parts and structures of those codes. Over time, you'll find patterns. Python programming is more like English, although there are rigid rules there, yes, but they follow some patterns. As well as when you get an error, you'll always get errors, bugs. When you debug, it takes some strategy as well. And over time, you'll find a better strategy. So those videos, make use of them. So I guess a bonus question for today. Now, since we're talking about neural network, and hopefully you have read something about neural networks or multi-layer perceptron model. So I'll just ask one question that goes a little bit into what we're talking about today. So can some raise your hand if you want to answer it? There's no penalty, but there's bonus. If somebody can give a fairly complete, not precise but accurate, sounds like the same concept. Anyway, at least not mistaken statements, fairly summary statements about what a multi-layer perceptron neural network model is. Let's go. Expiring soon. Well, no. I guess virtual students. Oh, no. A neural network model. Model. So a fairly doesn't have to be all inclusive. Fairly complete description or summary of what a new multi-layer perceptron model is. Uvi?
Is a forward model which when you give them there's divided into three layers. The first layer and it is consists of neurons and the neurons.
And all right, I think that's great. And you would start off with saying it's a supervised machine learning model that consists of a kind of standard structure as 3 layers input, hidden, and output layer. Information flow from input to the output layer, but the learning process will feedback from the output to the hidden layer. That's a fair summary. Great. Next word. What's your last name? Right. Great. All right. So that's what we are discussing. And if you were to compare logistic regression to MLP, MLP is multi-layer perceptron. Don't be confused with PML. What's PML? Python machine learning, which is the book. So we have, for logistic regression, we have the input, and we have a neuron that we call, right? And we have these weights, and those weights are basically attached to this neuron. That's kind of a single neuron layer. Single neuron layer. It's a layer, but it's very simple. And it outputs to the outcome, which makes predictions 1 or 0, right? So this is a simplified version of neural network in some sense. But when we expand the concept to multi-layer perceptron, then I don't mean that these input features expand in some way. They don't. They are basically the same. Of course, the model has different capabilities, right? So same input layers, but now we'll have at least expanded version of the input hidden layer, right? And we used to write I to indicate different. I is different data points. It's typically say this is the data. I is the data point, but we have this. J is to indicate different columns, different feature space, and we also have J to indicate different input features. That's the same. Then when we get to the net input, that's only one dimension, basically one single dimension, a singular. Summarize everything there and activate and then make predictions. But here it's going to be way more complex. If one of these neurons is like a logistic regression, then we have multiple logistic regressions parallel to each other to work. So the complexity of the logistic regression, if we have J goes all the way up to M, and here we have M times the number of neurons. So that's the amount of complexity that is being expended. And we typically say this is hidden layer. J, I use K, and K is all the way up to some notation. Hidden, I think I use D. So M times D, that becomes a matrix. And this matrix is going to store the coefficients. And it's not only the rows and columns, but also the off diagonal. It's not only a diagonal. Like we have M, we have D. It's not only a diagonal, but off diagonal. So many relationships going on here. The first input to the first neuron, the first input to the third neuron, the second input to the first neuron, second input to the second neuron, way more complex. And when information flows from the hidden, not the single neuron from in logistic regression to the output, it's a scalar for each data point. It's a single number. After activation, it's a single number. It's within the bound of 0 and 1 after activation, right? In logistic regression, and then according to the cutoff threshold, make a prediction. That's all. But think about the information that flows out of the hidden. We still have multiple dimensions of information, and here, different from logistic regression, we can now predict multiple labels that are typically what we say mutually exclusive. Think about classifying customer into high income, medium income, lower income bracket. When you don't have the income, and if you are able to predict the income profile of the household or head of household, that will be a lot informative in terms of to form your marketing strategy. So in that case, you have 3 brackets. One customer or household is only going to belong to one of these buckets, and you don't have to predict one logistic regression for this, one logistic regression for this. You can predict one neural network to predict all of them. So that's the advancement and complexity. And up to this and to this point, it's kind of like this stage of logistic regression. Each of the individual logistic regression start from the hidden layer, and after activating those values, this layer acts somewhat like the input layer, right? And to the first output neuron, it's like a logistic regression. For the second, it's also like a logistic regression. For the third as well. So in early stages, models are actually trained like that. Each of the output neurons are independent from each other, which makes it easier for backpropagation because it lowers the dimension. It's just several logistic regression models being trained. That's easier. But somehow I have to work out the sharing of the coefficients between the logistic regressions, but still that's easier. But you'll run into a situation where your activated value for this output, let's say higher income, the predicted confidence is 0.7, medium income, predicted confidence 0.6. You have a conflict. If you use 0.5 as a threshold, you have a conflict. Of course, you can compare them, but clearly there's something to be improved, right? So a better way is to use a different kind of activation function. We'll talk about the specifics, right? And over there, it's not only true or false, or 1 or 0, like in the case of sigmoid activation. Sigmoid activation is really imitating the confidence of one outcome or the other. But when you are working with multiple outcomes, you have these multi-class version of sigmoid, something like that. And then in there, it's going to impose a structure that the probability ijk, this jkl, the probability of L all over these dimensions is an output, so we use T, or maybe we use O. The predicted confidence over all the possible labels in the output layer is equal to 1. So when you have a high likelihood prediction, the others should drop. It will make very clear, clear implications and predictions of the case, and that works, much better than having individual logistic regression models. So that is some changes here. So our objective is to dig into the model, trace the information flow going through. We'll use this as the prototype. We'll only have time to work through I guess, the simplest deep neural network. It's deep neural network, but it's simplest. Still, it's deep neural network. And we'll use the virtual students. Can you see that this graph?
Yes.
3-layer MLP. Okay, so this is the kind of the structure we're talking about. There are multiple things that are flying here. It's not working. Oh, that's fine. Okay, anyway. So we have the input layer. We use J to indicate each of the individual, and the dimension goes up to M. And it's fully connected. It's fully connected. So that's why the dimension of this matrix would be M by D. Right? D is the dimension of the hidden layer. We use K to indicate individual neurons. And the output layer, use L to indicate. It can go up to T, and T can go to thousands for big neural nets. In our class, we typically deal with 2. So if T is 2, then we have 2 outcome predictions. And that's almost as if you're working with the logistic regression, right? So we work with this simple special case to understand the structure. But going from 1 to 2 is a huge difference. It requires a different mentality to understand it. But going from 2 to 5, that's just easier, much easier. So we use this as special case to prep ourselves to understand the structure. And if we have this structure where we have only 2 outcome labels, then you can, for sure, you can deduct that the prediction here, by use the multi-class, we call multi-class some name. Anyway, that the activation function, with that activation function, the sum of the prediction activated value will sum to 1. So if prediction is 0.7 here, then it's 0.3 over here. It's for sure. It's calculated that way. Any questions here? So let's compare. Look at the process here. So this is the process inside the loop. And recall that in Adeline model or logistic regression, we only have 6 steps, maybe, right? So let's do an exercise here. So let's think about, although we have these new names, they are just names that, make the complex problem less complex, put them into different perspectives, but they apply to simpler models as well. Once you understand neural network, when you look at the logistic regression, it's just a, simplified version of neural network. We used to not have the forward product, backward product, but I refer to them anyway, right? Because that's how information flows. It's very similar. And here, it's going to use gradient descent, same thing. Later, we'll have fancier versions of gradient descent, but that's just to overcome the complexity of neural networks. but the gist of that is the same. So, okay, let's go from the top to bottom. After we prepare the data set, we pre-process the data set. Deal with the data problem and understand the dimension of the data set. Data set doesn't change. It's m by m, right? And then it enters the network. The first thing it does is still the net input. It goes, so it goes into net input by multiplying input with the randomly generated coefficients. That's where the hidden layer is, where we calculate the net input, right? That's the first net input now. Information flows from input to the hidden layer. The hidden layer has d number of neurons. So this net input is not only one neuron, but multiple. So let's talk about that. Let's stay there. And for each of those input, they will activate. We begin with sigmoid. Later, we'll use more optimized version of activation functions. For now, we can use sigmoid. And for hidden layers, sigmoid always works. For output layer, not so much for neural networks, but for hidden layers, sigmoid always will work. It will slow down the learning process, but always works. So right there, it completes the first forward prop step. And after you have the sigmoid activated version of the input, it further propagates to the output. So that's why we have another net input that happens on the output layer. It takes information from the hidden layer, serving as kind of the input layer, but that's a hidden layer. Activated values from input layer goes into the output layer, goes through net input again, calculation, and then another activation. We still use sigmoid for now. Later we'll change it. And after this activation, what happens in logistic regression? Can you remember? What happens after activation? We calculate errors. Great. We calculate errors. The purpose of that is to calculate gradient descent. Gradient, right? Also, we will use the activated value. We can use that to make predictions, right? And use some threshold to make predictions. Same thing here. Same thing here. The purpose of the active value is twofold, right? To calculate the error in order to calculate the gradient, and also to make predictions. In terms of the gradient, the error that enters the backprop, and that's going to be more complex, way more complex. It has 4 steps to complete one backprop. Before we only have kind of one step, right? We calculate error. Be precise and pay attention to where this error is. This error happens on the outcome side, the output layer. It's the actual error that this model is currently making. Distance that the prediction of the model is from the ground truth. Right? In the first epoch, it's not going to be very close. It's random. So this error is kind of huge, but still, it can be improved. After you calculate the error of the output layer, you will need to calculate the error of the input layer. Backprop stops at input because you don't go all the way up to the data level because there's nothing to change in data, right? What you need to change are the coefficients that are in the hidden layer and the output layer. Two layers of coefficients that you need to change. Two matrix, basically, right? So you need two errors. The error on the output layer is very straightforward. You subtract the activated value from the ground truth. That's your error. That's all the error that you have, all the errors that this model is making. However, what is deciding the amount of this error? Not only the output layer, but the input layer as well. So we have to kind of find a way to define how much responsible is the hidden layer, not only the output layer. The output layer is bearing all the errors, but we have to find a way to pop back responsibilities. If this hidden neuron, if this hidden neuron is messing everything up, is messing, this is the bias. This is the first. If this neuron is making things worse to the greatest level, we have to fix it. We have to make sure that the gradient descent goes more extreme for this neuron than for other neurons, right? And if this neuron is making the biggest mess toward this output neuron, then first of all, this output neuron is going to have more errors in the first place. This prediction is going to make more mistakes. So here there are more errors calculated. And we want to make sure that the greatest amount of error, the biggest share of these errors will propagate through this link to this input neuron to change it. That's how it works. So so let me stop there. I'll talk more about how that happens shortly. So from the output layer to the input layer, it's the share of the error that will be calculated. So when you have the error of the output layer and error of the hidden layer, first of all, think about the structure, the layout of the error object. In logistic regression, you're going to subtract activated value from ground truth. What is the ground truth? It's y. It's one vector. So if you subtract one vector from the other vector, it's going to be a vector. So the error is a vector, right? Here, the error is a matrix that has a dimension of n number of rows, which is the same as the data set, which also is the same as the net input matrix. Data set, net inputs, and errors share the same structure according to the layer. The number of rows always the same. It's the number of data points, but the number of columns depends on which layer it is. So that's just to make sure you kind of think in that way. When you have the errors, with different layers and having different structures, then we use the error matrix of that particular layer to calculate the gradient for that particular layer. How does that calculate? We say that we want to make sure the neuron that's making the biggest mess gets the biggest responsibility and punishment in terms of, move it more, change it more to to drastically improve the model accordingly, right? Recall how you calculate gradient. Gradient, conceptually, it's the slope. If the slope is larger, it will change more. It will update the weights relatively more than another slope that is flatter. If the slope is flatter, it's almost close to the optimal solution, right? So that's all kind of proportional. So, and the way you calculate gradient, if you remember, use neural network, but it should be similar to the case of logistic regression. It's the dot multiplication between the weights transpose and the data, and the error, not the data, the error, right? So it's the dot, the NumPy dot, right? And two components. One of them is the current weight owed. The other is the error. Why do we do that? Hold on, no, not the, sorry, not the weights, the data set. Multiplication between the data set and the error. Let's check. Weight, data set and the error, right? So data set, error means how much distance, how much far off the current model is. If the error is huge, you do think the weight, the slope is steeper, right? If it's making a lot of errors, it's away from the optimal solution. The slope is steeper, that's for sure. You want it to be updated sooner, faster. And what role is the data making? The data in a standardized scale. If the data is standardized, then 2 is bigger than 1, right? 2 is bigger than 1. So when the data set are all standardized, then the data points will also govern how important they are. If one variable has bigger variations, the values are always 2 and -2. When standardized, there is a lot of variation going on, and this variable may be more influential than another variable that has less variance. So when you put those two information together, it's a gradient. And pretty much same thing here. When you have the error for the output layer is more straightforward. It's a subtraction between two terms. And when you calculate gradient, it's the basically the dot product of the error matrix and the data set. Well, not the data, the input layer activation, currently serving as like the input, data set, right? When you're working on backprop for the output layer, when you're working on backprop for the output layer, the hidden layer is serving somewhat like an input layer. And what are the data here? They are the activated value coming out of the input layer. That's the deal, right? So you calculate the gradient here by multiplying the activation functions going into the output layer with the errors that are making at the output layer. But when you're working with the backprop, calculating gradients for the input layer, you are multiplying the actual input data with the amount of error share that we calculated from earlier that this hidden layer is responsible for. That makes sense, right? So that's the whole backprop process. There's always two steps: the output and the hidden and the output. And these would be the toughest steps of training neural networks. After that, we calculate weight update. That's intuitive. Alpha learning rate times the gradient. That's mostly it. And then we update the weights. When we calculate cost, similar. It doesn't matter how many layers are there. The cost is directly related to the last activation function. So that's the same. And don't forget to save the cost into a cost value list. You want to save every step. Sometimes it's not every step. You can like skip steps. When you're training 500 epochs, you don't have to save 500 results. You can save every other. That's simple, engineering tricks. Score is when we calculate evaluation metrics like accuracy. And later we'll talk about false positives and false negatives. Those are more advanced evaluation metrics. Okay, so that's a complete neural network process. If you think that's interesting, that's not so complex, then you'll be surprised. But not really. I mean, you can do it for sure. It's just more steps to wrap your head around and try to understand. And you can do that. Any questions? I think I'm kind of done here. If you have particular questions, let's talk about those. Mostly about neural networks. In your reading, if you have questions, it's really no point for me to go too much ahead when you're not have no idea what I'm talking about. So it's better now for you to study and practice and study, have some questions, bring it back to the classroom. We'll talk about those. Okay. So next class we'll start. I mean, we'll probably discuss some of the conceptual questions, and we'll start talking about specific codes.